The technology evolution to 5G Advanced and beyond continues to expand mobile into new verticals and use cases. While 5G is scaling down to address the needs of lower complexity devices with NR Lite or RedCap, it's also evolving in dimensions to become more capable for those specific applications. In this video, we'll show how 5G Advanced IoT innovations can further extend network coverage and deliver efficient positioning for narrowband devices.
One key area for research is focusing on how 5G can be optimized for IoT services requiring wide area coverage. In this demonstration, we will look at how 5G device relays, utilizing co-channel sidelink, can enable effective outdoor and indoor coverage extension in a 5G network. To showcase this, we have set up our test network with a single small cell with 100 MHz channel bandwidth at 3.5 GHz on top of the garage. Its coverage is limited due to the low transmitted power of the small cell. There are several outdoor and indoor IoT sensors that need to connect to the network but are out of range. To facilitate this communication, multiple device relays are placed in between the small cell and the out-of-coverage IoT sensors. Note that all IoT devices share 5 MHz subband inside the cellular channel with compatible TDD patterns. As you can see, when we add device relays into the network, coverage is extended via multi-hop sidelink connections. The sensor data from the out-of-coverage device is shown to be efficiently relayed back to the network over multiple device hops. In this mesh network, there is routing support, which optimizes the best signal path for the out-of-coverage device to be connected to the network. For indoor devices that have no clear line of sight to GPS satellites, they can obtain GPS timing source from another connected device, and in this case, an outdoor device relay. In conclusion, device mesh networking can effectively extend the coverage for low-power IoT devices within the same cellular channel. It supports dynamic routing of data through relays and provides timing source for indoor devices. This technology can potentially make 5G IoT deployment more cost-efficient.
While we exploit the wide bandwidth nature of 5G to achieve high positioning accuracy, many 5G IoT devices like wearables and sensors will operate more efficiently with lower bandwidth. This means pure timing-based techniques do not work as well, since the narrow bandwidth reduces time domain resolution and network synchronization errors lead to less accurate positioning for device-based positioning methods that are suitable for IoT. To achieve improved positioning accuracy for narrowband devices, a device-based positioning technique like downlink angles of departure can be utilized. Based on the positioning reference signal sent from the base station, the device can estimate the angle of departure based on relative differences in beam RSRP or received signal strength, which is not sensitive to the reduced bandwidth. With multiple downlink AoD measurements, the positioning of the device can be determined. This demonstration utilizes our 3.5 GHz test network at our headquarters in San Diego, California, where we have 2 base stations on top of 2 different buildings. For each of the base stations, we have a massive MIMO implementation of 512 antennas. The system uses 5 MHz bandwidth to connect to several IoT devices that have direct line of sight to both base stations. Utilizing downlink AoD positioning technique in our over-the-air testing with multiple devices, we can see the average positioning error across different device locations on the left-hand side of the GUI. Let's click into one of the devices. Here we can see more positioning information of the system, including the positioning estimates of the device, and the median and the 80th percentile errors are also shown on the left panel of the GUI. In conclusion, multi-cell downlink AoD is a positioning solution that can deliver cost-efficient, low-power and wide area positioning for a large number of narrowband 5G devices.